In this lesson, we're going to characterize the dose and dose rates that we should see from this residual radiation that we discussed in the previous lesson. Now, first, we're going to look at a quick rule of thumb, and that's on this slide here. And basically what this says is that we can get a factor of 10 reduction every 7 hours, every power of 7 hours following our initial detonation. So what does that mean? Well, okay, so it means that 7 hours after a detonation occurs, say we have some dose rate. In this particular example, we have it at 100 rems per hour. Now, if we go 7 times 7 hours, or 49 hours later, we then see that it has dropped down by a factor of 10. So we've gone from 100 rems per hour down to 10 rems per hour. If we then multiply by an additional 7, so 7 cubed, we see that this is about 14 days, and this will reduce our dose rate down further by another factor of 10 to what you see here, which is about 1 rem per hour. So if we take 7 and we keep raising the power of it, every time we raise the power of 7, we end up with a number of hours, and then we end up also with a cumulative reduction. And so the corresponding numbers, I'm just going to read them out. I'm not going to write them. So for 7 hours, you get no reduction. At 49 hours, you get a reduction by a factor of 10. At 14 days, you get a reduction factor of 100. And then it kind of goes out a lot further there. And so about 3.5 months later, you get a further reduction by another factor of 10. So now you're at a reduction of a factor of 1,000. Now we're into the years. 1.9 years later, you're at 10,000 reduction. And then finally, if we go all the way out to 13, about 13 and a half years, we've reduced by a factor of 100,000. So time, when talking about exposure, it's not only important to know how long you were exposed to this residual radiation, but it's also important to know how much time has elapsed since it was created. So since we detonated our nuclear device, the longer we wait, the more those radioactive materials are going to decay, through their chains to become something stable to reduce the overall amount of radioactivity that's present. So again, if you wait long enough, you'll be okay. It's why places like the two places that have actually seen a nuclear detonation, like Hiroshima and Nagasaki, people live there now and they're fine. Chernobyl's a bit different. Chernobyl had a heck of a lot more radiation released. So it is taking you can get a reduction factor. It's been years. So you can even get a reduction factor of 1,000, but you have to, compare that to the amount of radiation that was released in total. So while something like Hiroshima and Nagasaki are back to normal by this point, it's going to be still many more years before the area around Pripyat and the Chernobyl power plants returns to normal. Okay, so the next thing we're going to look at here are these charts out of the book. These are figures 9.16a and b, and this is similar to what we've done before. We're going to use these to look at some examples of how you can get some information and then use charts to figure out information that you may need. And I think for the rest of this, we're just going to use the examples that are presented in the book so you can follow right along. Now, these charts are based off of, we'll call it somewhat incomplete information. These are based off of like the 300 most common isotopes produced in the wake of a nuclear detonation. So it's not entirely 100% inclusive, but again, we can call it close enough. So the example in the book is at 15 hours following detonation, we see an exposure rate of 4 rads per hour. Okay, so we're going to use a chart to read this. However, I must point out there are two different lines on this chart. We have a dotted line and we have a solid line. Okay, now the dotted line is basically, it's a theoretical calculation. It uses an equation, and that's why the line's pretty straight. Now what we see is the solid line is what they've actually measured, experimental data. And we see the solid line, it kind of bobs and weaves around the dotted line, but it's pretty close. All the way out to about a month here. However, what we see here is right around 6 months, we're going to see a huge divergence between what we actually see and, you know, this fitted line that matches the experimental data. And that is, we see a very large divergence after 6 months. So that's where our theoretical fit model tends to fail. And it gets worse as we move into the years and 100-year regimes. So anyway, how do we use this? Okay, so the first thing we're going to do is we're going to say, okay, well, what information were we given? Well, we were given the information that at 15 hours, the dose rate that we're seeing is 4 rads per hour. And if you see me looking down, it's because I've got this written down on a separate little sticky note on my on my computer screen. Okay, so the first thing we want to do is we want to use this to figure out, well, what's our, this is dose rate, unit time reference dose rate. So how do we use this to figure out what we need to know? Okay, so what we're going to do is we're going to come here and look at time after explosion. So the time after explosion is going to be at 15 hours. So we got 10, 20, so 15 is right here. And so we're just going to come up and we're going to see where that intersects, which is, we'll call it right about here. Get out of there. Okay, so this is 4. Now please make sure when you look at these charts to look at the values on the y-axis, because if you wrote down 4, you would be wrong, because so this is 4 times 10 to the minus 2. Okay, so this is going to be equal to 0.04. Okay, so now we have 2 different numbers. Okay, we had our 3 different numbers. We had our 15 hours, which is the time after explosion, and then we had some sort of dose rate, which is 4. So we used this chart to figure out, what's the dose rate over the reference dose rate, and we get 0.04. So how do we figure out, well, what does this mean and how do I use it? Well, we now have, I'm going to pause this. So how do we use this value? Well, we can take this and multiply it by the dose rate that we have in order to figure out, well, what's this reference dose rate that we're looking for? No, sorry, other way around. Damn it. So how do we use this value? Well, what we're reading here, this is going to be dose rate over some reference dose rate. Okay, so we know our dose rate, this is going to be equal to the 4 rads per hour that we were given. Okay, so now if we want to, and what we just read off the chart is going to be our dose rate over our dose reference, and that's equal to our 0.04. So if we wanted to figure out what our reference dose was, right? So we just divide the dose that we have by our reference dose, and what we end up coming out with is a reference dose Okay, so how do we use this? Well, say we were looking for our dose rate at 24 hours following our detonation. So we would come over here and we'd say, okay, well, one day, right here. So that's 24 hours. We read up to here. And this is going to be at about a bit higher. So this is going to be, again, we're 2 decimal places over. So this is going to be about, I don't know, 0.02. And the book uses a value that's much more accurate than this. The book uses 0.023. 0.02 is just fine. Okay, so now we know, now once again, we have a d over d ref. And this is going to be some dose that we're looking for, right, over our reference dose. Going to run out of space. So that's going to be equal to our 0.023 times 100. So we're just going to put the decimal in there, which is going to be equal to about 2.3 rads per hour. Okay, so that's how you use these charts, and you would use whichever one had the time scale that you were looking for, either from the first thing that you're given or towards some arbitrary time in the future that you need to calculate from. Again, though, be aware that if you use this chart right here, that you're using the solid line and not the dotted line. Okay, there's another way that we can do this instead of reading from a chart, doing a calculation, reading from a chart, doing another calculation. So for this is very much like we saw with the damage to the buildings, right? So we had some axes, we drew a line, and we read off some figure. That type of chart, and this one as well, is called a nomograph. So what we're going to do here is we have an exposure rate, and then we have the amount of time that it was done in. So we're just going to connect the dots, and then we're going to be able to read what our reference dose is. So if we connect our 15 hours to our 4 rads per hour, we find our reference dose is crossing right here at 100 rads per hour, which matches up to what we just found with the previous graphs. So no giant surprise here, but it is nice to see that you can get the same result from 2 different sources. Now, if we were looking at 24 hours later, we know the reference dose is 100, right? So whatever line that we draw, it's going to have to hit 2 numbers, right? It's going to have to hit the time of 24, and it's going to have to cross through the value, our reference value of 100. And then we can find out what the dose rate is. So if we do that, right there, ta-da, we can see that, yeah, it's 2 and some change. Now, doing the math might give you a little bit better of an estimation because you have actual values to work with. In this one, you're kind of eyeballing it. But again, it's all approximation anyway. So whichever method that you choose to use, that's fine. If this is being done for a homework assignment, just for whatever the problem happens to be, say which of these 2 methods you used. Or there could be a homework assignment that just has you do it both ways and compare what your end results are. But again, that's how you use this chart. All you're doing is drawing lines, not doing any kind of math. All right, so let's look at this graph, which is figure 9.20 in your book. Now this is figuring out accumulated dose, not just dose rate. So we want to know how much radiation did we actually absorb, for a particular amount of time. So we have on one axis is time after explosion, of course, and the second axis is accumulated dose, right? But then it's also looking at our reference dose rate, which we figured out before. So following the example in the book, we're looking at 2 hours after detonation. We've measured a dose rate of 1.5 rads per hour. So we're probably going to have to use one of those 2 previous methods that we just looked at in order to figure out, well, what's our reference dose rate? So I'm going to use the first 2 figures that we looked at. Okay, and let's look at time after explosion in hours. And we're going to look at 2 hours, and we're going to come up here. I already drew the red line. So this is going to be, again, we're at 10 to the minus 1. So this is going to be 0.4. So we know from before the way that we can use this now with the dose rate that we already have to get our reference dose rate, or DREF. That's going to be equal to the dose rate we measured divided by our reference dose rate, which is going to be equal to 3.8 rads per hour. Okay, so we read that right off of this chart. So far, easy peasy lemon squeezy. So let's go back to the figure 9.20, 9.20. All right, so we're going to look at, well, what's the figure of merit that we're looking at? Well, there's two of them that we're looking at, right? So we can say, well, first of all, we're looking at 2 hours. I'm just going to mark it here. All right, and then we're looking for 12 hours after that, which is 14 hours, which is going to be somewhere right around, we'll call it right here. So let's read the figures off here. This is going to be 7 and a little bit of change, and this one is going to be 5 and some change. So let's call it 7.2. Where's my thing? There it is. So let's look. So this is going to be our accumulated over reference. So this is going to be equal to, we'll call it 7.2. And the one down here is going to be equal to about, 5.7. That's a pretty good estimate. The book is a little bit different. The book says that this is 7.1 for the book, and says that this one is 5.8. Again, they're much more accurate at reading these than my poor eyes can do. So if we want to know what the scaled accumulated dose over unit time reference dose rate for 12 hours after the explosion, we're going to subtract these two numbers. So we have 7.1 minus 5.8, and that's going to give a total of 1. I can't do simple math. This is 1.3. Okay. So now we have our reference, our accumulated dose over our reference dose rate. Accumulated dose. And we know what our reference dose rate is because we've already found out. Our reference dose rate is going to be 3.8. And that's going to give us a total answer of 4.9 rads. Accumulated dose from 2 to 14 hours following our nuclear detonation. Okay, and that's how you use this chart. You can say, all right, well, if I start here and I end here, in the time following the detonation, how much dose am I going to accumulate based off of, some reading that I took at some point, which will correspond to a reference dose. And that's it. And you could have done this just as easily using the nomograph that we saw before. So let's go ahead and look at an example that does use the nomograph. So in this figure, we're going to look at how do we find an exposure between when we, the time that we entered the radiation area after the detonation occurred for some arbitrary length of time. So what we're going to do is we're going to look at yet another example in the book. Now the example I'm using is that we have a measurement that was taken 4 hours after detonation occurred where we got a exposure rate of 6 rads per hour. So let's go ahead and figure out what our reference dose rate is, right? So our reference dose rate, instead of using the charts the figures that we just used, let's use the one that we can just draw a line on and see how that works out. Okay, so external rate, dose rate from early fallout. So we know that we're going to have to draw a line between 6 over here, that's our dose rate, and our time over here, which is 4. So let's do that. And we can read off a unit time reference dose rate of we'll call it 30 rads per hour. I think the book calls it 32, but again, my eyes aren't that great. So we have our reference dose rate of 32 rads per hour. So let's go back to here. So the question in the book says, all right, I want to know if I went in at 6 hours and I stayed for 2 hours, what's going to be my accumulated dose? Well, let's look at entry time, time after explosion. Let's look at 6 hours, which is right about here. Okay, and then we're staying for 2 hours, so we're going to read right up to this curve here. And this is going to give us a multiplication factor, a dose rate multiplication factor of, again, make sure you remember this, 0.2. So our multiplication factor, let's just call it M, is equal to 0.2. We have our reference dose rate, right, which we found out to be, we approximated it at 30. The book says, no, it's more like 32. Oh, that should be an R, not an S. Okay, so then we're going to say, using my multiplication factor and the total and the reference dose rate that I already have, if I multiply them together, we get 6.1 rads. So if we went in 6 hours post detonation, we stayed for 2 hours. This is how much dose we would accumulate during that time based off of a reference dose of that we calculated from a measurement at 4 hours, which was 6 rads per hour, which gave us about 30 rads per hour reference. Pretty straightforward, at least I hope so. So that's kind of all I really wanted to talk about. There was another figure. There is another figure in your book, which is this figure right here. This is used in a very similar manner. I was going to talk about it, but I think I'm going to go ahead and let you look at it and the example that the book provides that goes with it. So that wraps it up for this set of lessons. The next 2 lessons or sets of lessons that we're going to cover to round out the course is we're going to be looking at high altitude effects, things like electromagnetic pulse, looking at nuclear winter, and then finally we're going to look into the topic of survivability where nuclear weapons are concerned.